All right, for our next presentation, we have, Ilya will go now. Okay, so we're swapping the schedule a little bit. Dr. Ilya Kolb will come here, and while he's setting up his slides, I will introduce him. So Ilya comes to us for the second time. He gave a fantastic speech last year, and he works for a remarkable company that you all should know about called Aromyx, Aromyx. They have sponsored our conference here. They're our first sponsors, and we are absolutely thrilled to have them here. We feel that what they do is important for many reasons. They do create odor and flavor palettes that can be used to reproduce or even replace human noses and human tasting panels. You need help?
Yeah, do I need to HDMI or anything?
Yeah, no, HDMI is fine. Here. There. Wireless. Actually, but you should do the HDMI one. Maybe we should have someone from MIT AV come and help with this while I'm talking here. You actually have a HDMI. And so he'll tell you all about how their technology is evolving and how you can measure smell and taste to guide product development. This is the first out of a few speeches that we have from companies, including people such as Tunable, who's another sponsor. So I want everyone to pay attention to the fact that olfaction and flavor are connected, and that these are the last frontiers in the perception game. And whoever is playing this game right now is at the very early stages, but Aromyx is already dominating, and they've done something that I feel eventually will be able to be used for much more than just food and drink, including disease detection and who knows what else. So with that, I'll let Ilya tell you all about it. Thank you for coming here. And this is Ilya Kolb from Aromyx. Thank you.
Thanks, Andreas. Great to be here in person for the second iteration of this conference. So today, I'm going to talk to you all about how we at Aromyx have a platform to measure smell and taste to guide product development. So why do we concern ourselves about being able to quantitatively evaluate smell and taste? So as I'm sure most of you can appreciate, these are things that are extremely important for a huge amount of products that are coming on the market. But so I have here examples of fragrances, food and beverages, consumer packaged goods, which are all billion, multi-billion, and trillion-dollar industries. But the main problem that these industries face is that the way in which these products get developed is really kind of straightforward. They have sensory panels where they ask 20 people about, oh, do you like this fragrance? Do you like this new coffee? They say, yes, this is great. It goes on the market, and then it fails horribly. So the statistic that we like to point out is that between 75 to 95% of new products actually fail in the marketplace. And I think part of that is because there's just insufficient testing going on and insufficient quantitative information available about these products. And so we at Aromyx think that having quantitative insights into smell and taste beyond kind of the standard consumer panels would actually revolutionize the way that these companies develop their products. So a little bit about the receptor biology. This may be kind of relevant for those of you who may not be familiar with it. So this is basically how we as humans perceive smells. Here I'm going to, for the remainder of this talk, I'm going to focus on smells because that's what this conference is about, even though we at Aromyx also have a lot to do with taste. But for olfactory receptors, these are the receptors that line sort of the inside of your nose. And this is the primary way in which odor molecules interact with our brains, basically. So the odor molecule binds to the receptor, which is lining the membrane of a neuron, and this is the neuron that projects back up to the brain, and this is how you perceive things like lemon and cherry and mint and so on. There are about 400 types of different olfactory receptors in humans, and as I mentioned, this is basically how we sense things in the world. So what's really kind of fascinating about the olfactory code and the way that in which we perceive smell is how this all actually works. So you would think that, or the straightforward solution would be that you have one particular odor molecule that triggers a neuron and you smell lemon. You have another one that triggers another neuron and you smell mint. But that's actually not how it works. In fact, it's a combinatorial code, which means that if you have sort of this plume of smoke that has all these different molecules in it, different receptors will bind to different molecules, and it's really the combination of neurons that triggers a particular percept. So it could be that these three neurons activate and you smell lemon, and then the same neuron activates, but a different one activates at the same time and you smell mint. And that's what enables our measly 400 olfactory receptors to discriminate from thousands and potentially millions of different odors. You can think about it as if you have a piano with something like 90 keys, you can make a ton, an infinite amount of music with just those 90 keys, and it's really the same way in the olfactory system. So why do we at Aromics really care about studying things on the olfactory receptor level? And it's because what we think is that these receptors are sitting kind of really in a nice place between the odorant space on the top here and the perception space. And the key for us in terms of making sense of what how odorants influence perception is this idea of dimensionality reduction. So if you think about the odorant space, there are hundreds and thousands of different kinds of molecules that are very hard to categorize into groups. And because of that, you can think about them having a huge number of dimensions. The cool thing about olfactory receptors is that they are a natural way that the brain and biology has found to reduce that dimensionality down into something that is actually more relevant to our perception. So on the other hand, we have actually on the perception level, you have these consumer panels where people say, okay, I like this product because it's sweet, I dislike this because it's bitter. And of course, this is great, but it's not very quantitative. So we think that us being kind of on this middle level of studying the receptor level actually allows us to be able to bridge these two disciplines or these two sort of kinds of study together. So just a little bit about how our platform works. I don't have time to go into too much detail on this, but we do the best we can to mimic what the natural human smelling process is like. So this is kind of how it works on the human perception level. We have the receptors that bind the odorants. There's a second messenger system that gets involved, and then that signal gets sent to the brain. And then in our system, we have, the important thing is that this primary machinery here is all exactly the same. And then the only thing that's different is that we have a light signal that gets emitted that tells us whether a particular receptor is getting activated. So I'll just share with you two use cases of our technology. So first one is going to be about using this receptor data to create flavor mixtures. And then the second one is going to be about detecting malodors. So in the first use case, what we're looking at here is a mixture that we know smells like passion fruit. And so what you're seeing here is a panel of receptors. So the receptors are the columns here, and the rows are the mixture that I mentioned, and then 3 individual ingredients in this mixture. And the really cool thing about this is that, so what you're seeing here is basically the light green to dark green represents these different receptors being activated in response to the mixture or the individual ingredients. And what's cool is that, at least in these, the first 6 of these receptors, we can see that we can clearly see how each ingredient is contributing to the mixture. So, for example, in this chemical, it doesn't matter what the chemicals are right now, but this chemical, we can see these 2 receptors are contributing the same receptor activity to the passion fruit mixture. This ingredient is contributing these 2 receptors. So we can see that the mixture is actually a pretty linear combination of the ingredients with some notable exceptions, for example, this AR70. So the cool application of this is that we can now, knowing this, we can do kind of in silico flavor matching ingredient replacements and additions. So as an example of ingredient replacement, if one of the ingredients becomes extremely expensive or we run out of it, we can in silico make models and try to predict what alternative ingredients we could use in order to replace that ingredient. So the second case I'll talk about is malodor detection. And here we had a customer that had a batch process that produced malodor in some of their batches. Unfortunately, I can't reveal who the customer is or their particular application, but suffice it to say that they tried using GCMS, but they found that, unfortunately, GCMS, while they were able to see signals from it, it just wasn't predictive of whether that particular batch would have a malodor or not. And so they contacted us to see if we could use our receptors to actually be able to detect the malodors. And what the data here is showing is activity from 3 of our receptors. This is just a subset of what we tested. And what we're seeing here is the responses of these receptors to a control batch with no known malodor, and then 3 known malodorous batches that we call M1, 2, and 3. And what this is showing is that basically we have at least one receptor that is pretty robustly responding to all of these 3 malodorous batches, and they're not responding at all to the control non-malodorous batch. So extending this a little bit further and saying, okay, can we actually use this in an industrial context to be able to discriminate malodorous batches? We found that we have that for malodorous batches 1 and 2, or batches like those, we can detect them with over 97% accuracy. Now, with malodor batch 3, the accuracy is much, much worse, so there is still some development needed to be done there. But this is already kind of an improvement over the existing gold standard practice in that field, which is just people actually smelling the batches one after the other, which of course is not very scalable. So really excited about this direction in the field and looking to pursue it further. So just closing up to tell you a little bit about kind of where we are and where we're going. So we have worked with over 40 commercial projects to date with dozens of different commercial partners. And we've characterized at this point over 600 individual products. Most of them were in the last year, or last 2 years or so. And I just really like this visualization on the right. You can't really see it super well here, but basically this is just a representative kind of example of 41 receptors as the columns, and then over 400 products that we've tested as the individual rows. And hopefully you can appreciate kind of the really wild diversity of receptor responses that we're seeing here. And the way that we're able to do all this is a lot of automation and process development. So we're able to, at this point, screen between 40 to 80 samples or different products per week, which is up from 10 to 20 products that we were screening at this time last year when I gave this talk. So this is, so the throughput is really something that we've worked really hard on, and I think we've made a lot of progress on. We've made a lot of progress also on taste receptors, which I haven't gotten the chance to talk about here. And yeah, as I mentioned, we are using this receptor technology for all sorts of new product development, reformulations with individual ingredients, and quality control applications. So with that, I would like to thank our group, mostly Kenny Joseph, who did a lot of the experiments that I showed here, as well as our data science team, Bradley, Dean, and Sen, and the rest of the folks over at Aromics. So thank you very much.
That was wonderful. Thank you so much. I always get a huge thrill out of seeing olfactory receptors at work in a completely industrial setting outside of their natural environment. This should give us all hope that they can actually do this. Many years ago, my sort of, I always loved Aromics. I thought they were ahead of the game. I always tried to help them. But many years ago, I had this comment that, oh my God, you must be so brave to be able to deal with the finicky cells. So I want to ask you this. How hard is it? What is the day-to-day of having to keep these cells alive? Because my nightmare is, having done this before, my nightmare is that this is a little bit like having a canary in the coal mine, only the canary is constantly dying from other causes, and you don't know what they're doing. Yeah. So have you experienced a lot of that?
Yes, definitely the canary is always dying. Biology does not like to cooperate, and that's what we found, and that's really why really our focus for the last year has actually been mostly on throughput, because originally when we were kind of, many years ago when the company started, it took a PhD scientist to be able to keep the cells alive, do the assay, do the transfections, do the data analysis. And really the challenge for us has been over the last couple of years to industrialize it and make it so that it's really just a reliable process. So I think, the real story here is process development and making things really, really robust, making all sorts of quality control, systems. So yeah, making it robust has really been the key. I can't say that we've entirely solved it by any stretch of the imagination, but I think we've made enough progress to where, we have the numbers, we have the kind of throughput to kind of show it.
Hi, so we have a question from the chat. Joseph Izzarelli wanted to know how the odorant molecules are delivered to your platform, gas, vapor, or are they dissolved into a liquid medium and then delivered to the assay?
We do both. So we typically look at either delivering the molecules in the gas phase or the liquid phase. It really depends on kind of what produces the best responses. But yeah, we definitely do both.
Great, thank you so much.
I have another question, Ilya. And forgive me for being a lawyer again, but it seems to me that you are standardizing the receptor detection in some ways. And if I can kind of mention, in law, we usually don't have direct evidence. We usually have circumstantial evidence, which is, it sounds to me, something of what you're doing. And we use the reasonable, prudent person standard. When you kind of do this the perception detection, are you trying to kind of standardize the basic receptor elements to identify these types of odors?
Yes. So that's basically exactly what we're doing, because, the way that we think about it, the signals that we see with the receptors, to us, like, this is the sort of the ground truth. So this is the information that's actually going into your brain, right? And so everything that, so the complicated thing is that, different people will perceive things very differently, right? Like, I might find a smell disgusting and somebody else might find it very pleasant, but the receptor data going into both of our brains is exactly the same. And so we think that by measuring things at the receptor level, like, this is the best place to actually be able to start to make predictions about what people's perceptions will actually be. So yeah, I think we treat this as kind of like, this is the missing link between the odorant molecules and the perception.
Yeah, thank you.
There's another question.
Please.
As you mentioned, the human nose has more than 400 different olfactory receptors. How many different receptors do you guys use? And maybe a better question is, how many do you really need in order to get a pretty good idea of what a scent profile is?
Yeah, that is a great question. So one of the main challenges in the field is that these receptors are very difficult to express in heterologous cells, which is exactly what we use. The answer is, we don't really know yet. So we don't know we know that the distribution of receptors is non-uniform in the nose. So there's kind of a power law distribution of a few receptors being expressed very, very widely, and then less, and then even less than that. It's not quite, all we know right now is, we can differentiate certain products. I think the proof here has to be in the kind of actual testing, right? So if we can differentiate, for example, a sugar-free beverage from a full sugar beverage, then okay, for that application, we have enough receptors, we can clearly tell the difference. There may be another application where we can't differentiate that on the receptor level. And that's when we know, hey, we don't have the right receptors to do that. So it really has to kind of vary case by case for now.
Thank you.
One last question for Ilya here. The community of osmonauts, as we call ourselves here, including yourself now, people interested in smell and dealing with these technologies, we're all very impressed with Aromics. And I want to ask on behalf of the community and myself, where does it hurt? Where should we be focusing to help businesses like yours? Where can you help the researchers sort of guide their work or perhaps give us some direction as to what is the next frontier? Where does it hurt more than anywhere else that we can adjust to make the biggest splash in this?
Yeah, I'm really glad you asked that, because that is actually, I mean, that is one of my main reasons for coming here, and kind of one of the main reasons that we want to keep interacting with the scientific community. Where it hurts them, I mean, one of the pain points definitely, and I think you already kind of alluded to that, is, you know, we have to deal with the biology, right? We have to use these living cells, which are very finicky. So definitely being able to somehow get olfactory receptors on out of an incubator onto a chip, something that's portable. You know, we love to explore that. You know, I think that's something that we would be very interested in partnering with people on. And also just a lot of basic science. I mean, the previous question, I think, you know, we don't have all the receptors working. We definitely want to get all of them working. So I think we're looking for basically ideas about how do we, on a basic science level, how do we get more of these things to work? How do we get more reproducible signals, higher signals that are easier to detect? So that's, I would say, the pain point. Like I think what we've kind of solved at our company is the scalability, right? So like we can test a lot of things, but where we kind of would love to partner with people is on the basic science side.
So please keep interacting with our community here, and for our community and our listeners online, there's many of you who are entrepreneurs and business people in general. Here's a business that has actually led the way and has the highest chance of creating the entire human palate, I think, is with Aromics. Nobody else comes close. So please do, let's all help them get to where they're getting, because the amount of benefit that we're going to get as a community of scientists, but also as a society from what they're doing is immense. And it's exactly relevant to what we're doing. So with great big thanks to Aromics for their sponsorship and for this wonderful lecture. We have 2.5 days of this. Please interact with us and let's see how we can help them and how they can help us. Thank you again.
Thank you very much.